Hi, this is Dr. Green. We're doing some examples for the week 4 problems here. First up, we are doing a confidence interval. So our researchers here are trying to find out the mean concentration level of a pesticide in strawberries. The researchers select a sample of size 20. That is going to be our value of n right here. And then they find that the sample has a mean of 2.4 micrograms, so that's x bar right here. And then the standard deviation is 0.8. So that's S, and that is right here. And then we're calculating a 99% confidence interval for the mean. So that's this formula here. The only value that we don't know is Z. And then this formula comes from table 622. So if we go over here to table 622, we have one sample. They've only given us information for one sample. And then these pesticide values are continuous. They're not success failure. There's not just two outcomes. That would be dichotomous. So one sample continuous, right there is our formula. So now we need that Z value that goes with 99% confidence. That can be found in table 1B. So you go back here. Here's table 1B. Our confidence level is 99%. The Z value that goes with that is 2.576. So that's right here. So now we go ahead and do our plug-in. So X bar out in front, that's 2.4 plus or minus that Z value of 2.576, and then times S over square root of n. So our S is 0.8, and then divide by the square root of 20. So you might want to do this portion in your calculator first, and that's what I did. I got 0.461. So this is actually then 2.4 plus or minus 0.461. So 2.4 minus 0.461 will be 1.739. That's the lower limit. I'm sorry, that's 1.939. And then 2.4 plus 0.461 is 2.861. And I've recorded those down here as the lower limit and the upper limit. So our interpretation of this is going to be that we are 99% confident that the true mean pesticide level in the population is between these two cutoffs here, which is the 1.939 micrograms and 2.861 micrograms. In problem number 2 here, researchers looking at, again, means here, mean C-reactive protein levels in two populations, so it's going to be a different formula, of individuals who are diabetic and individuals who are not diabetic. So the mean C-reactive protein or CRP level for the sample of individuals who are diabetic is 15.6. So that's going to be our first mean. So this is the mean of the sample. So that's going to be X1 bar. That's down here. And the standard deviation of that sample is 4.9. So that's going to be S1. And 35 individuals here were in that sample. That's going to be N1. That's our sample size. And then the mean CRP level for individuals who are not diabetic is 5.8 with a standard deviation of 3.9 and 30 individuals. So X2 is 5.8, S2 is 3.9, and N2 is 30. Now notice here that both of these sample sizes here are greater than or equal to 30. and that's going to be important when we look at the formula here. So from table 6.22, we've got 2 independent samples, diabetics and non-diabetics, and C-reactive protein levels are continuous. So we go back to our table here. Let's see here, 2 independent samples and continuous, okay, which is this formula right here. So notice that we've got that value S sub P in there. Okay, so that formula is back in the chapter. That's right here. So N1 and N2, S1 and S2, those are our sample sizes, which we have here. And this is what's called the pooled estimate for the standard deviation, because you're using both the estimate for the first sample and the second sample. You only use that when both of those samples are greater than or equal to 30 in size. And if you do the plugins here of this information, so our N1 is 35, that goes right here and right here. Our S1 squared 4.9 gets squared there. N2 is the sample size of 30, goes in here and here. And then S2, which gets squared on the end, is the 3.9 right there. Compute that in your calculator, you will get approximately 4.468. And then we need a z-value that's going to go with 95% confidence here. So that's, again, table 1b. So we slip back there, table 1b. We wanted 95% confidence now, so that's 1.96. So z now 1.96. So now we're ready to go ahead and do our plugins into, this is the formula from table 622. I just brought it down here. So we've got the difference of those two means, which is going to be 15.6 minus 5.8, and then plus or minus that z value of 1.96, and then times the times S sub p, which is the 4.468, and then times the square root of 1 over the first sample size, so that's going to be 1 over 35, plus 1 over that second sample size, which is 1 over 30. So again, I calculate this in my calculator, multiply by the 4.4, multiply by the 1.96. So when I did that, I got 2.18, and this difference is 9.8. So this gives us 9.8 plus or minus a difference of 2.18. So you do 9.8 minus 2.18, and that will give you 7.62. And then you do 9.8 plus 2.18, which will give you 11.18. I'm sorry, 98. So add and subtract that. Margin of error is what that quantity is. So our lower limit, 7.62, upper limit, 11.98. Our interpretation, we are 95% confident that the true mean difference between the population C-reactive protein levels for diabetics to non-diabetics is between that 7.62 and the 11.98. And remember what that means is if you keep taking repeated samples for 95% of those samples, the true population mean difference is going to be inside these cutoffs here. In our third problem, we are calculating a point estimate for a phase 3 clinical trial for medication used to treat RA. 1,285 patients showed improvement of their symptoms, and 329 individuals did not show improvement. So we've got successes here and failures, okay? And our point estimate here is going to be the sample proportion, because this is a dichotomous outcome. This is a binomial experiment. So the sample proportion is p hat, which is successes over the total sample size. Well, the successes here were people that showed improvement in their symptoms. That was the 1285, so that goes up on top. And then the failures were the 329. They did not show improvement. So they've got to get our total sample size, they've got to get added on there. So we do the 1285 plus the 329. And then if you compute that on your calculator, you will get 0.7962. So that is our point estimate. It's a single value that's estimating that population proportion. You could also equally well write this as a percent. In example number 4 here, we've got a phase 3 clinical trial for a new medication that's going to treat fibromyalgia, chronic pain syndrome. 855 participants were in total. All of these individuals were from the group of individuals who were given the medication. So that's our treatment group. And 568 individuals who received the medication experienced improvement in their symptoms. Okay, so 568 is the improvement, that's successes, 855 is our total. And they want us to construct an 80% confidence interval for the proportion of individuals who experienced improvement. Okay, so this is one sample here. We've only got one sample. Either they, that was 568, and that sample, either they improved or they didn't improve. I'm sorry, one sample, 855. And then these were the improvements, the successes. So that's a dichotomous outcome. Either improve or you don't improve. And so if we go back to our table of formulas here, we've got one sample dichotomous outcome right there, p hat plus or minus z, and then the standard error there is square root of p hat, 1 minus p hat over n. So that's this formula here. And then we need that p hat, which is successes out of the sample size. That was our 855 was our total sample size. And then out of that sample, we had 568 that experienced improvement. So if you compute that on your calculator, you'll get 0.644. And then the z-value we're going to get from table 1b, we want 80% confidence. So you go back to that table. 80% confidence down here on the bottom. 1.282 is our z-value. And so now let's do our plugins here. So 0.644 is our p hat out in front, right there, plus or minus. Our z-value is the 1.282, and then square root the 0.644, and then times 1 minus that 0.644. That's probability of failure. So it's probability of success, probability of failure, and then we're dividing by that whole sample size, which is our 855. So again, on your calculator, compute the square root first, multiply by the 1.282. When you do that, you'll get 0.021. So this is 0.644 plus or minus 0.021. So we do 0.644 subtract the 0.021. We will get 0.643. And then the 0.644, add the 0.021, get 0.685. So we're 80% confident. They didn't ask us for an interpretation on this one, but we're 80% confident that the true population proportion is in this interval. That means 80% of repeated samples would contain that true population mean. All right, and our last question here, last example, and then you should be raring to go on those problems, is a researcher compares the hemoglobin A1C for two populations here. So it's a two population interval from different ethnic backgrounds here. We find that the proportion of individuals that are considered diabetic from Caucasian population is 0.28. So that's actually your p-hat for the first population. And they tell us n is 180. So that's the first sample size. So down here, when we start filling in p1 hat, x1 over n1, we don't know what x1 is, but they gave us the whole sample proportion there, 0.28. And then they also gave us that the first sample size is 180. So let's fill that in here. Always got to write down your givens. And then the proportion of individuals that are diabetic from non-Caucasian population is 0.22. Sample size is 98. So this P2 hat is 0.22. N2 is 98. Now to get our formula here, go back here to our table 622. So now we have two samples and dichotomous outcome, success, failure. That's this one right here. Or no, I'm sorry, that's confidence interval for the risk reduction. So let's see here. No, that's what we want. Risk difference. I'm sorry. We go back to the problem here. They want a 90% confidence interval for the risk difference for diabetes from Caucasian to non-Caucasian. So that's RD is risk difference. And then we've got two other here. So the odds ratio here. And let's see, I believe that's risk reduction. Okay, but we're doing risk difference. Okay. So that's this formula here. So I pulled that over and I pulled it down here. And then we've got a z-value here that's going to go with 90% confidence. We get that from table 1b. So we're going to go back to table 1b. 90% confidence right there, 1.645. So this guy is 1.645. And so now we go ahead and do our plug-ins here. So the difference of the two proportions goes out in front. So 0.28 minus 0.22 plus or minus that z-value of 1.645. And then a bunch of stuff under that square root. So we've got that 0.28 is P1, and then 1 minus 0.28. Divide that by the first sample size, which is the 180. And then do the same thing for the second population. So that success probability was 0.22, and failure would be 1 minus 0.22. And we're dividing by sample size, which was 98. So it's going to be a little bit careful when you're calculating this. So you want to calculate what's inside square root first, take square root, multiply by 1.645. And when I did that, I got 0.088. So this is 0.06. So I got 0.06 plus or minus, and then 0.088 to 3 decimal places. And so you are going to subtract the 0.088 and then add the 0.088. So this goes from negative 0.024 up to positive 0.148. And we're 90% confident that our risk difference is inside this interval. And notice that interval contains 0, so that means that we can't make a conclusion about whether our risk difference is greater than 0 or less than 0. Okay, so you should be able to finish up all of the problems for homework 4.